In this lecture, I shall teach you in another aspect that how we can design the solar panel or PV cell, or it is called photovoltaic cells, steel supporting structural arrangement. So as an example, you can just Google this PV solar panels steel structure. So here you can see that this is the typical arrangement when the solar panels are ground mounted. So here you can see the solar panels just taking supports from the ground, and after that here there is an example in which when they are mounted along the roof. So here also you can see that this is basically the roof, and then they are just supported over the roof along the profile of the roof. So in short, there are four types of supporting for the solar panels. This is the website of landpowersolar.com. Here they have given this example that either they can be pitched roof mounting system, that is they are just supported along the pitch of the roof. So here you can see that they are just supported along the sheet. So whatever shall be the slope of the roof, it shall be the slope of the solar panels also. Well, obviously the direction of the sun is also important. So this is basically the flat roof mounted system. So in case we have an RCC building on which the roof is just a plain roof, so on that this is the arrangement which we should propose. And in this arrangement also there are various types of further arrangements. That is, the number one is the portrait ballasted mounting. Second thing is the adjustable portrait mounting. Third is the landscape ballasted mounting. Fourth is adjustable landscape mounting, and fifth is the east or west ballasted mounting. That is, the solar panels are raised, are sloped along both the sides. So all these are single rows, and orientation is also important. That is, in this it is basically the portrait arrangement, and in this it is basically the landscape arrangement. So that is why it is named as portrait, and this is named as landscape ballasted mounting. And the reason for this two row is basically when we need much more efficiency. So in that case we can install two solar panels in the landscape orientation, and it is called two row landscape mounting. So this was just an introduction of how we can support the solar panels. Third is the again the ground mounted system. So in the ground mounted also, you must have seen various airports also which uses the solar electricity from the solar panels. So if you have visited the Cochin airport in Kerala, India, the whole airport is being run by the solar power. That is a very great thing. And when we take off from the airport or land at the airport, you will see that there is a very large solar farm installed there. So it is basically the number one option is the all portrait ground mounting. That is the basically all the solar panels are installed along the portrait mode. Second is the landscape ground mounting. That is, they are installed along the landscape. Then it is C channel steel ground mounting. Pile driven ground mounting, that is, it is just a single pole and from which there are two cantilevers here. This one is the solar pole mounting. So you must have seen various light poles. So for light poles, what they do is that they install a light pole over this PV cell system. So on a single pole they install this solar panel also, and as well as they install a light pole also. And after that there is this another versatile arrangement, that is angle manually adjustable ground mounting. That is, the angle of this ground mounting system can be adjusted. And the last one is the carpet mounting system. So here you can see that they have installed this the whole solar panels along the sheeting. So whatever be the slope of this open sloped roof mounting system, it shall be the slope of this steel structure supporting sheet. So in simple words, the slope of steel structure is equal to the slope of the solar panels. So this is basically the various types of arrangement that we can use. So in addition to the making a this car parking, in addition we can have this area used for the generation of the solar panel electricity also. So you can see how much versatile we can go ahead. So there are various further options when when we are designing the steel structure for the solar panels also, we need to take a nominal loading of 20 kg per meter square, and that too I am taking that on the higher side itself, because usually the loading of the solar panels comes out in the range of 15 kg per meter square. So that is 0.15 kilonewton per meter square. But as an on the conservative side, in this example we will take the weight of the solar panels to be 20 kg per meter square. So in this example I shall like to go ahead with this type of arrangement. That is it is a ground mounted system, and there are basically this three numbers of cells that can be installed here. So we shall model a simple steel structure, and then we shall model the cold form steel structure arrangement, and then we shall apply the wind load, and then we'll try to analyze and design it as per the India standards. So first of all, we shall open the STAAD editor file, and then we shall enter units as meter and kilonewton, and then we shall enter the joint coordinates as origin. And then after that we shall model a structure like this. So here we can assume the height of this structure or this column to be nearby 0.75 meter, and here we can take the height of this as 1.5 meter, and this distance we can assume it to be approximately in the range of 3 meters. So this is the general profile. Here I have taken this distance as 3 meters, this distance as 0.75, and this distance as 1.5 meters. So now basically we need to further make some additional columns. So here the approach that they had considered is that the width of this arrangement, that is the width of solar panels, they have taken some offsets here. So as a general practice, what we can make here is that we can just repeat this whole structure after 3 meters. So here we can model the secondary beams, and here we need to geometry add beam between midpoints here. So this is the general arrangement, and further you can see in the example that there are some cantilevers also. So that is also general practice in the case of this solar panel mounted equipment supporting steel structures. So what now we can do for making this cantilever offset in the slope of this member. So this is also a very unique approach. So what we can do is that we can offset this column by, let us say, 0.5 meter here. So after that what we can do is that we can select this beam here, and then we need to go to geometry and stretch selected members. So here we need to select it to an existing member, and we need to select this member name, so we can name it as 14 and apply. So with this approach you can see that the member is just offsetted of 0.75 meter along the slope of this line. So this was also just a small hack that I use whenever I encounter this type of situation, and similarly we need to do the same approach here. So what we can do here, we can just copy this column and we can select Z as minus 0.75, and now basically if the slope we shall see it will go up also. So for that case what we need to do is that we need to select this node, geometry, move, joint, and we can select it as 1 meter. So with this approach what we can see that now the height of the member has increased, and now we can easily stretch this selected member. So geometry, stretch selected members, and the name of the member is beam number 17, and we need to left click on apply. So after that we can delete this particular column here, because the purpose of this like member is solved. So this was just a simple approach that we can follow, and after that we can copy this member along x as 1.5 and then again to 3 meters. So I hope the things are now clear that how we can make this type of arrangement here. And after that is the most important thing is that as the members of the street structure are very much fragile, so we need to make this type of bracings also. And after that, what some people do is that to like decrease the loading here, they also make some bracings here also, so that the weight of this member is reduced, or the loading on this member is reduced. So that we will see in the further optimization. But before that, I want to put the like model the whole structural steel arrangement, and then we shall think of how we can optimize this like project here. So after that, what we need to do is that we need to release the members here also. So first of all, we can release the column members also. So we select beam, release start my and mz, and then we need to go to beam end and my and mz. So here basically all the points are the end points. This is the starting point. So first of all, we release the arrangement here, and then we can release the arrangement here also. And then after that, we don't need to like apply the release here, because this is a single member from this point to this point. This is also a very important approach. So here you can see that this member is resting on the top of this member, so we don't need to like apply a release here. So here, as this is here, you can see that a plate is installed on the bottom of this, or on the interface of this member and the columns here. So that is why I had applied release here, so that all the bending moments are balanced on the top itself, and only axial forces will be transferred from the upper supporting arrangement to the columns here. So here we don't need to apply the releases here. Here we can apply the release. So here also you can see that they had modeled this bracing arrangement here, and they had modeled this bracing arrangement here also. So basically the purpose of here, you can see that they had like transferred the load from this point to this point. So this is also another good approach. So here also you can see the loading being transferred here. So that we will discuss in the further optimizations, but now I think the bracing part is okay. And after that, what we can do is that we can assign the supporting arrangement also. So we need to assign pinned supports only. We cannot assign fixed supports here. So that is done. After that, in the specification also, all the specifications are done, and after that we can apply the properties also. So we need to go to section database here. Here we can see that this column is basically a double channel here. So we need to apply double channel here. After that, we need to apply a single channel here. And in the form of bracing also, they have applied a small channel, but we can apply angle or channel if required. So first of all, we need to go to cold form steel, and then we can go to Indian cold form and channel. And in the case of channel, we can left click on view table. So the depth is the criteria here. So as a starting point, we can select this 100 depth channel here. Left click on select here, and then select a double channel arrangement here. We can select the spacing as 0.05 here. So this arrangement needs to be a double channel here. And further, they have made some offset here also. So what we can do here is that we can just select x as minus 0.5 here, and then we can model these beams. We need to apply vertical offsets also in the specification, but that we will do later on after deciding the depth of all these members here. So first of all, we need to apply double box channel arrangement to this particular beam here. After that we can apply single channels to these beams. The length of this channel is approximately 3 meters. So it is suggested that we need to go with minimum this 100 mm or 75 mm depth also for channel. So we select cold form steel, Indian cold form and channel. Here they have taken the basically single channel with lips. So we can also go ahead with single channel with lips. So in the table we can see the depth here. So the depth in like as per my conception it should be minimum 90 mm. So we can select this particular channel here and then left click on add here, and then we can select all these beams here. So now the beams are also assigned properties. After that we need to assign the circular member property here. Here we can see that these members are circular. So basically you must be thinking why they have applied circular member properties here. Because circular members have equal amount of moment of inertia along both the major axis as well as along the minor axis. So when the forces will either come along this direction or it will either come along this direction, we don't need to worry about, because in both the directions the moment of inertia or the section modulus of the circular sections are same. So that is an added advantage of why we like use this circular pipes as a steel structures. And you must be thinking why we use this type of arrangement in the light poles also, because in both the directions the forces are same, so the section modulus required for the structural steel sections are also same. So to have the most economical and to have the most efficient section, that is why we use circular sections for the light poles also. So after that we need to go to the section database. Cold form steel, and then we can select this. Here we can see that there are no sections available for the pipe sections, so we can go ahead with this, and we can define the outside diameter and inside diameters. Tubes are basically the rectangular hollow sections, and these the pipes are the circular hollow sections. This is also an important concept that we are talking about here. So the outside diameter and inside diameter. So basically if we model a simple circle in the AutoCAD software, so this is the outside diameter and this is the inside diameter. So we do need to take the simple math. So let us suppose we want to make a 4-inch or 100 mm outside pipe. So for that, if let us suppose we take the thickness of pipe as 2 mm, so the inside diameter shall be 96 mm and outside diameter shall be 100 mm. You do need to take care of the situation here. That is, if this is 96 and this is 100, so the thickness of this section shall be 2 mm. So this is just a simple math, and let's move on to the start file here. So here we can select outside diameter as 0.1 and inside diameter as 0.096, that is 96 mm and 100 mm. So left click on add here and then apply here. And if required, maybe it do happens that the STAAD may not design these circular columns for the Indian sections. So in that case we can also go ahead with AISI, but that we will discuss in the later stages. And after that we do need to apply the angle sections also, or we can take the channel section also for this arrangement. So let's select cold form steel, Indian cold form, and select the channel here. So after that we can take the depth of the channel as 70 cu 44 and then left click on add here. So now we have assigned all the properties, and to make the structure somewhat repetitive, we can repeat this whole structure along the x-axis. So the distance that we do need to repeat is 3 meters. So we can select translational repeat, and then x, default step spacing as 3 meter and number of steps as 2. So, and then after that we do need another offset here also. So in this case what we can do is that this whole arrangement can be mirrored about this particular point here, as this is 4.5 meter here. So we select this generate mirror option, mirror plane as YZ, node on this particular plane, and then just copy this arrangement. So we have try to model this simple arrangement here, and then after that we do need to apply the loads also. So left click on add here, loading type as dead, then we need to select live, then we need to select wind load along X and wind load along Z. So I am not applying the seismic loads because they might not matter in this small steel structure, but I had already taught you how we can apply this earthquake loading for the Indian standards. So that is why I am not repeating the arrangement here. My approach is to teach you how we can correctly model this type of steel structure arrangement, how we can apply wind loadings, and how we can analyze and design a cold form steel structure as per the Indian standards. So left click on add here, and then we can go ahead with self weight. Why we can select it as 0.05 for the connections and another steel structures arrangement that might be welded to the top of this arrangement here. And then after that we do need to apply the solar panel loading also. So for solar panel we can make a flow load here. So for applying flow load we do need to apply the group also. So we need to make a floor name here. So we can name it as group number 1, select type as floor, and then left click on OK here. Here we can select the members here, but the problem is that the loading may not be applied on this part and this part here. So to avoid that approach, what we need to do is that we need to apply the uniformly distributed load along these beams here. So what we can do for that is that we can just open the calculator here. So if we want to apply 20 kg per meter square dead load of the solar panel along the direction of gravity, and our typical span is 1.5 meter here. So for this beam, it shall be responsible for taking 0.75 meter loading on the left and 0.75 meter loading on the right. So the total span for this beam shall be 1.5 meter, and so shall be for all the remaining beams. So if we are talking about 0.2 kilonewton per meter square, 20 kg per meter square, so 0.2 into 1.5. So the dead load for the solar panel shall be 0.3 kilonewton per meter along the direction of gravity. So we can select it as member load, uniform force, and minus 0.3. And then it shall be direction in the not local y, but it shall be in the global y direction. So we shall select all the beams here, or what we can do is that we can just select all the beams from this option, go to view selected objects only, and then again go to the load cases and details to save our time. You can go to labels, scales, apply immediately, and distributed force. So the direction of loading is applied in the direction of the earth gravity, not in the local direction. Here, just as in trial, we can also apply this. So here we can see that the angle changed, and when we apply the global y direction, it is in the direction of this. So that is the difference between this y local and global y direction here. And then after that, the live loading shall not be that much on the top of the solar panels, cause no one climb on the top of the solar panel. So live loading is of basically no use to us. And then after that we need to check it for the wind loading arrangement. So for wind load, what we need to do is that we can apply the wind loading along the direction of x also, as well as along the direction of z. But along the direction of z, wind loading is the dominant. So we shall learn how we can apply wind loading for this in the next lecture.